what I want to do, this was a lot, so maybe you might want to take a pause, take a 20-minute to an hour break, or maybe even take the night and do the rest of these examples later. But what we're going to do next is just we're going to practice with the rest of our data in Excel. So we'll go back to this workbook. We're going to work with the grades data. We're going to work with the growth data. And we're going to practice using, doing this regression analysis and using the output to make some statements about these, the relationship between these variables based on the sample that we've been provided. All right, moving on to our second example. We're in the W13 Day 2 workbook. As before, we want to move to the sheet called GRDS, short for grades. And here I have some fictitious data where I'm essentially looking at the distance that a student sits to the board and their exam grade. So what I want to explore here is there a relationship between how far someone is sitting to the board in a classroom and how well they do in the class? So I'm using exam grade to measure how well they do in the class. And, obviously I'm just measuring this in, whatever it happens to be, feet, etc. So the first thing that we're asked to do here is visualize the data, show a trend line, the regression line equation, and the R-squared value. So what we're going to do with these examples is, as before, I want you to, periodically pause the video, try to do it on your own, right? Give yourself an option to self-test. And then if you do it, great, check your answer when you hit play again. If you get stuck, that's fine, perfectly natural. It's your first couple times through this. Just watch the solution and kind of follow along and fill in the results. All right, so pause the video, try doing this visualization part first. All right, good. So remember, for our scatter plot, we highlight all of the data. So I just did a Control-Shift down. We insert our scatter plot. Here's a look at the exam data is on the y-axis here, and that, remember, is usually the column to the left. And the distance to the board is sitting over on the x-axis, and this is usually the column over to the left. And we can kind of see that it looks like these dots are generally following a negative sloping line, meaning the people who are sitting closer to the board tend to do better. Let's see how good of a fit this is by adding the trend line and the R-squared value. If you want to, you could add a chart title here, exam grade versus distance to the board. Remember to add our trend line, once we're clicked inside of the chart in the chart design ribbon, we go to add chart element, trend line, and we always go to more trend line options because down at the bottom we have the ability to display the equation of our regression line on the chart and to display our R-squared value. Okay, so in this case we have an R-squared value of 0.78. This is pretty close to 1, so this is a pretty strong relationship, pretty strong correlation. We can look at the correlation coefficient in a minute. As we kind of observed before, we do have a negative slope for this regression line, meaning that the closer you sit, the higher your grade. And in fact, for each foot that you move away, we're expecting about a drop of about 2 points in your grade. Okay. So we're done with part 1. The next part involves using our data analysis tool pack, and what we want to do is regress exam grade onto distance to board. And we're going to use a confidence level of 93%. Now, the language here, regress this variable onto the other. The first variable is assumed to be your y variable. So for our y variable, we're going to put in our exam grade data, and for our x variable, we're going to put in the distance to board data. All right, so self-test, go into your data ribbon, try to do the regression analysis. Remember, we want to set a confidence level of 93%, and typically you want to make sure that you also check the boxes for the normal probability plot and the residual plot, because those are our diagnostic plots which tell us whether we can trust the regression. So pause the video and do this. All right. So remember, inside our data ribbon, all the way to the right, there should be a data analysis button. If we click that button, a dialog box opens up. We want to select regression because that's the technique we're going to use. We get a new dialog box where we can put in our data ranges. The y variable is our exam grade, so we're going to do B3 to B68. The x variable is our distance to board, so that would be A3 to A68. According to our problem, we want to set a confidence level of 93%. And remember, this confidence level is used to compute our confidence intervals for the slope and intercept terms, which is an important output that we're going to talk about in a second here. So let's call this grades regression. It's going to go out into a new workbook. And let's take a look at the residual plot and the normal probability plot. These are our two diagnostic plots. All right, and let's hit OK. So we have our usual output here. We have our normal probability plot, and we have our residual plot. It's a good idea to look at these first because there's really no point in kind of interpreting all of the rest of this information if we have reason via these two plots to suspect that we shouldn't trust the regression results anyways. Here it looks like we have some random scatter for our residual plot, so that's good news. And the normal probability plot, these do tend to be following a line, so it looks like everything is working for this particular regression analysis. We can now sort of avoid those plots. If you want to, take a second here and just go through and gray out the stuff that you don't want to use. So for example, I know I'm probably not going to use my adjusted R squared, so I'm just going to gray this thing out. Oops, there we go. I'm just going to gray this thing out so that kind of mentally, it tells me I can sort of ignore that stuff. So pause the video and gray out the other stuff that we don't typically use in this class, and let's check back in and make sure we have the same stuff grayed out. All right, good. So for the regression statistics, I really only care about multiple R. This is going to be the magnitude of my Pearson correlation coefficient. R squared is our usual R squared value, and this is our sample size, 66. We don't typically use, in this class anyways, anything from the ANOVA table, so we can gray that out. And in terms of the coefficients table, we don't really care about the standard error or the test statistic. We are going to be interested in some of these p-values. These coefficients are the estimates that the estimates for the slope and intercept term based on the data, and we have confidence intervals for the slope and the intercept, which sort of lifts that sample estimate up to a population level. So this is what we have kind of grayed out. Let's jump back into our other worksheet and see what kind of questions we want to answer. So we're back in grades. What percentage of the variation in exam grades can be explained by the linear relationship to the distance the student sits from the board? So in other words, keep in mind exam grades here is our y variable. We want to know how much of the variation in the y variable can be explained by these changes that we see in the x variable. So pause the video, see if you can get the right answer here. All right. Hopefully you remembered that this percent of explained variation is related to our R squared value. We can either pull our R squared value from this plot up here, but just as a quick reminder, if you want, you can pull it off of your regression analysis. So the quick way to pull data from your regression output into whatever worksheet you're working is to use cell references. So in this case, I can hit the equals button in the cell where I want some information, pop over to my regression analysis, and I can pull my R squared value by just clicking on the cell and hitting enter. So my R squared value has now been placed over here, and it's referencing my regression output. Now I can write my sentence. So we believe 78.4% of the variation in exam grades can be explained by the distance a student sits to the board. Now, obviously, this is fake data, right? The distance that you sit to a board is not going to explain your grade to such a high degree, but this is how we would interpret that particular statistic. All right, question number 3, is there a significant correlation between exam grades and the distance to the board? Using a significance level of 3%, or use a significance level of 3% and explain your answer. So the key here that I want you to focus on is there a significant correlation between exam grades and the distance to the board. And significant is secretly referring to a hypothesis test. Is there a correlation? Is there a non-zero correlation at the population level? So pause the video. We've done a couple of examples of these. This time I want you to use your regression analysis output to justify whether we have a significant correlation in this case. Pause the video and give it a shot. Okay, good. So the first thing you might want to do is just actually take a look at what your correlation is. You can either do the Pearson command here. So what would this be? B3 to B68, A3 to A68. We'll get a negative 0.885. Or the other thing you can do is pop into your regression worksheet, and you'll see here that the magnitude is a 0.885, and the slope coefficient is negative. So from here, we can conclude that our actual correlation coefficient is actually going to be a negative correlation. So we'll put a negative sign in, and then we can just cell reference the magnitude. So we could return it from our worksheet this way. Either way, this is relatively close to -1, so we know this is a strong relationship, but is it significant at the population level? Right? So in other words, we want to look at a p-value for a hypothesis test. Now, as we explained in the previous example, this particular p-value here does double duty. Remember, let's insert our comment here. This p-value not only tests the null hypothesis that slope is equal to 0, but also tests the null hypothesis that our population level correlation coefficient is equal to 0. So we can look to this p-value, which is very, very, very small, and we'll see that in a second. We can look to this p-value to make a claim about whether or not our correlation at the population level is equal to 0. When this p-value is small, right? So when the p-value is less than whatever alpha value we're setting or whatever significance level we're using, we reject these null hypotheses in both of them. So this means the slope at the population level is not 0. And for the other one, rejecting that null hypothesis means that the correlation at the population level is what we call significant. And what we mean by that is it's significantly different than 0. Now in our case, I'm just going to make this a little bit bigger here. Change this thing to a number, and you'll see that it's essentially 0. In fact, there's going to be 23 zeros before we start to see some sort of numerical content here. So this is like a 0.0000000 blah 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 0.58, an exceedingly small p-value. So certainly it's going to be under a significance level of 3%. So in our case, we're setting alpha equal to 0.03. And you can even test this. You can say, is this less than 0.03? And Excel will tell you, yes, it is. So the way we'd finish this problem is we would say, since the p-value for our significance test for correlation is below 3%, we do have a significant correlation at the population level. All right? And again, you might want to leave yourself just a little bit of a note here. Oops, sorry. You might want to leave yourself just a little bit of a note what that means. All right, so this means the correlation is significantly different than 0. Okay, so we have a non-zero correlation. In other words, there is some sort of relationship between the distance a student sits to the board and their exam grade at the population level.